As we learned with electron configurations, it gives us a way to give the probable location of electrons, and also gave us some very important information about our core electrons and our valence electrons. Those electrons on the outer shell that are going to give us the most information about our reactivity, physical, and chemical properties. If we look at these valence electrons and we look at the periodic table, we're going to see some striking similarities. Let's focus on our main group elements. And to start, let's look at group 1A. That's hydrogen, lithium, sodium, potassium. If we look at the electron configurations for this group, we start with hydrogen with a 1s1, lithium 2s1, sodium 3s1, and potassium 4s1. You'll notice that the valence electrons, the outer electrons, are always s1. What's changing is the energy levels. This gives us some very important information. We know that we are going to have a spherical outside shell because they're all s. We also know that this orbital is only half filled, only one electron and not two electrons. The other thing that's important to understand about group 1A is it also tells us something about the reactivity. Which ion is actually going to be the most likely ion? One of the things that we haven't talked about in depth is the Octet Rule. It's often referred to the Octet Rule because it looks at 8 electrons. But it's better to understand the Octet Rule from the standpoint of full shells. Why, whenever we get past and have core electrons, do we then move on to the valence shell? That's because those become stabilized. And once we get to a stable core, then we start to get the next valence. Well, what are the stable core? Well, our noble gases. Those things with a full shell at both the S and P, and later on when we get further into the periodic table, S, P, and D, and even further, S, P, D, and F. To get a noble type gas configuration for our group 1A, which is S1, we have two possibilities. We could gain 7 electrons, or we could lose 1. A little easier to lose 1 than to gain 7. So therefore, the most likely ion for lithium is not lithium minus 7, but lithium plus 1. What does that mean for the electron configuration? If we think about the full electron configuration for lithium, 1s2, 2s1, if lithium loses 1 electron, it'll go back to 1s2. Well, what element has an electron configuration of 1s2? It's helium. This is called an isoelectric electron configuration. Our elements, when they create ions, want to have an isoelectric configuration like our noble gases. Let's look at another group, group 7A. These are our halogens: fluorine, chlorine, bromine, and iodine. What does the valence electrons look like? Well, in that case, we start with 2. 2s2, 2p5. If we go down to chlorine, 3s2, 3p5. So the commonality here is that we're going to have a filled S, S2, and 5 electrons in our p shape. If we think about the isoelectric element, if we added 1 electron to fluorine, we'll have the same electron configuration as neon. So therefore, our halogens are much more likely going to gain 1 electron to become anions than they would to lose 7 electrons to become a cation. You can see here how looking at the electron configurations in the periodic table allow us to not only see the similarities in the electron nature of our groups, but also predict which elements would prefer to be cations and which elements would prefer to be anions. And not only that, but whether they will have a cation of +1, +2, or +3, or anions of -1, -2, and -3.